Thank you very much. I will give a talk in which I will try to explain the latest and last, unfortunately, paper of Frank, which I'm honored to be a co-author of, but also I'll try to highlight more than 10 years of joint collaboration. I'm very honored to be here today. And I have an initial page of things that are somewhat known to most people in the audience, but I put it there just so that we are all on the same page. And also, it gives me the chance to tell you a bit about the first result I had with Frank. So, a simplicial complex, just so that we're all on the same page, is something finite for today, okay? I know that some of you care about infinite simplicial complexes, infinite graphs, but today everything is finite. And finite collection of simplices, any two of which intersects at a common face. So the one-dimensional case would be graphs. I picture two simplicial complexes here. And a free face, so again, so that we agree on the definition, is a non-empty face that only belongs to one other face. Okay, non-empty because basically the reason of this non-empty is that I like normal homology more than reduced homology. If you like reduced homology more, if you would like a contractible space to have all zeros homologies, then probably you want to get rid of this non-empty from the definition. You're fine. Yeah. So, but for me, non-empty face contains only one other face. So in graphs, what I'm talking about, leaves. Okay. Above, you have a few free faces that in the PDF are red, but somehow the projector does not appreciate my red color, so they're difficult to see. However, these four edges here are free because they belong, each one of them belongs to one triangle only. And here you have lots of free faces. You have 9. 8 edges from the square above, 8 edges from the square below, and also this vertex here that belongs to this antenna, okay? It belongs to one edge only, so that's good. I'm going to talk today about elementary collapses, which is deletions of free faces. When you delete a face, you also delete everything above. So the one-dimensional case, I'm removing a leaf from a graph. As you can see, so this is what happens when you do an elementary collapse. And this is also what happens when you do an elementary collapse. Yeah, I picked one free face and deleted it. How? Randomly, basically. You can see from these pictures that purity is not preserved. And also non-purity is not preserved. Because, so this is pure, this is not. This is non-pure, this is. Purity means all inclusion maximal faces, called facets, have the same dimension. So it's not pure because this edge here is a facet that has dimension 1, and the other facets are triangles. So purity is not preserved, non-purity is not preserved. The homeomorphism type is also not preserved because you can see that this complex, topologically, this can be disconnected by killing this vertex, whereas this can't be disconnected by killing any point, so these two are not homeomorphic. So what is preserved? The homotopy type. Yeah, you can imagine a hand that pushes this edge inside, squeezes it so that, yeah, this retracts to this one. And similarly, this antenna you retract, and this deformation retracts to this one. So this is the only thing that gets preserved, the homotopy type. So I'm going to be talking about collapsible complexes. That's just a code word for a complex that can be reduced to a point via some sequence of elementary collapses. That means repeatedly killing one free face. And if a complex can be reduced to a point by a sequence of steps, none of which changes homotopy, then pretty surely this complex was already contractible to start with, no? Because if you can bring it to a point with steps and no steps changes homotopy, it means that at the beginning you have the same homotopy of a point. So because of this, collapsible implies contractible. The converse is well known since the 60s to be, actually probably was known from before the 60s to be false, but the most famous counterexample was given by Zeeman. It's called the band set, that was mentioned before. As a cell complex, that's a description. Just take a triangle and identify the boundary, put arrows identifying the boundary in any way you want it, as long as you avoid like cycling or so. And if you want a triangulation, I display the smallest one on the right, Bacci and Data verified that you can't do better than this one. This is triangulation with 8 vertices. intuitively, like in this corner, no? If you glue this edge with this edge, then I need to chop down this corner into at least 3 triangles, of course, because otherwise I would violate the definition of simplicial complex. Any 2 triangles must intersect in a common face, not in 2 edges, 1 edge. So you need, this corner has to be divided in at least 3. And this corner also at least 3. It turns out that this corner you can do it with 2 triangles, because, yeah, okay. So that's the best possible is 8 vertices. Okay, here I started working with Frank. So it was 2008, 2009. I was a PhD student. And for some reason, I think my advisor, Günter Ziegler, had a paper to referee, and he gave it to me and said, why don't you work with another student of mine that in the meantime has become professor. He lives like 4 floors below in the same building, because Technische Universität in Berlin has different floors assigned to different professors. So Frank was in the knot theory part of the building. I said, why don't you work with him? So this way you learn how to referee a paper, basically. And so Frank was of invaluable help. Was very, and we basically became friends. We started talking about problems together. And somehow, verifying this thing, we figured out something new. It was published in 2013 because it took long to correct everything and so on, or to get it past the editors. One of the editors is here. Yeah. So what we proved is that basically you can draw. It's pretty easy to see that this can be realized in R3 bending things. But what was not known is that you can draw it directly linearly in R3 with straight edges. The second new thing is that if you added edges, triangles, and tetrahedra, but no further vertex, so this could be inflated, somehow thickened, this better word perhaps, to a 3-ball with the same number of vertices. Second new thing. And third new thing is that if you looked at this new 3-ball, this 3-ball with one sequence collapsed to a point, and with another sequence of elementary collapses would get stuck in distance set. So this, by the way, this proves automatically that this is one way to prove that this is contractible, because a ball collapses to each, not changing homotopy type. So maybe I should say, why is this not collapsible? It's not collapsible because you're stuck in the very beginning. There's no free edge. The edges from the inside belong to 2 triangles. The edges from the outside, due to this triple identification, belong to 3 triangles. So there is no edge that belongs to 1 triangle only. So when you start doing elementary collapses, you're stuck at the very beginning. Any questions on this? Okay. I'm going to explain now discrete. I'm very happy about the talk of Michael Yosvi before me, because it looked like we agreed on what topics to cover. We did not. We did not talk beforehand, but I left out exactly the parts that he mentioned, basically. So it's very useful. I'm going to define discrete Morse functions now without using Charlie's characterization, which is what he explained on matchings. So I'm going to give you another interpretation. I'm going to give you a simplified definition. So first of all, this is what a discrete Morse function is. These are 2 simplicial complexes. I'm just going to shoot numbers on the faces, okay? The definition I give is not the original one. If you feel like confused, it's different but equivalent. So essentially equivalent, okay? Anyway, so I'm shooting numbers on all the faces. So every face gets a number, subject to 3 conditions. 1, weakly increasing, which means, so if a face is containing another, the larger face gets a larger number. Weakly, so possibly the numbers are the same. The second condition, I'm allowed repetition, but only once. In other words, I can use the same level at most twice. Okay? So you see that some numbers are repeated, but no number is repeated 3 times. So far you can teach it also at elementary school, right? And the third axiom and last one is even simpler. So this is supposed to be generic, meaning that if you have something that satisfies the first 2 but not the third, you perturb it a bit, it will satisfy the third. You perturb it exactly at the point, at the faces where it's wrong, you get the third. The third property is whenever 2 faces are assigned the same label, one of them is contained in the other. So if this is not the case, perturb a little bit the function, they will have different labels. So then this is automatically true because this gets false. Okay? So this, in 2 examples, you have them above. And let's call critical phases. The beauty of this definition is that it's very simple and also allows me in a very elementary manner to tell you what critical phases are. They are just the phases at which the function is injective. Okay, so in other words, those phases that get a label that is exclusive. No one else has it. For example, here, how many critical phases there are with respect to this choice of labels? One, right? This point here, which is red in my PDF. This time, actually, I think the projector liked my red. Over here, I think half and half. So there's supposed to be two critical phases. This one, which the projector likes, and there's also another, this is supposed to be red. Okay? I hope you see it red. Or maybe I'm getting color myself. Okay, so there's an important result by Forman, which is as follows. So first of all, I need to tell you what this Morse vector is. Typically, is that it counts the number of critical phases dimension by dimension. So in this example, like here, 1, 0, 0, because there's one critical vertex, 0 critical edges, 0 critical triangles. And over here, instead, it will be 1, 1, 0, because it's one critical point, one critical edge, 0 critical triangles. So a priori, this would be like, you could view this as an infinite vector, but then it's all zeros from a certain point, because of course, critical phases are phases. And so if you have 0 phases, you also have 0 critical phases. So if you have a complex of dimension 2, there's no reason to continue this vector. So it's all zeros after that. Yeah. So it has the measure is just a dimension. Actually, it has the number of entries is a dimension plus 1 because you start counting from 0. Okay, so the theorem by Forman is that if you want to understand a simplicial complex up to homotopy, all you need to look into are the critical phases. So this toy game here reveals to you information, full information about the homotopy. So what's the idea to prove this? I can sketch it to you in 2 minutes or so. The idea is to view a discrete Morse function as a sequence of steps. And each step can either be an elementary collapse or the deletion of a top dimensional phase. Okay? So how? When you look at the maximum of the function, there are 2 cases, and I highlighted just this happen to be the 2 cases. The maximum here is 5, no? The largest level. And it's repeated twice. Here the largest level is 7 and it's repeated once. These are the only 2 situations that can occur, right? Because no number is repeated 3 times. So the largest number is either repeated once or not repeated at all. If it's repeated once, it's very easy to see that this is a situation of a free phase because of the actions I've given you. So the 2 equal numbers, one must be a phase of the other, but also there cannot be here another triangle, because what value would you put on this triangle? It's supposed to be greater or equal than 5, but 5 was the maximum, so then 5, but it cannot be, you would have three faces with a 5. That's against my other axiom. So clearly, it's a situation of a free phase, which means you can get rid of both without changing homotopy, because of the previous slides. Okay, so if at the top you have this situation, you can get rid of both. And if you get rid of both with an elementary collapse, the other rather absolutely natural thing, obvious from the definition, is that the restriction of a discrete Morse function is still a discrete Morse function. So these numbers here on the complex with these 2 faces deleted, this is still a discrete Morse function. Think about the actions. One was like no number is repeated 3 times. This is obviously passes to a subcomplex, this property. And same for the others. It's completely obvious if you see it about 2 seconds. And so this way you can keep going. When instead you have a top dimensional phase that is a critical phase, well, you can delete it, but then you delete it by itself and you're supposed to remember this step, because this does change the homotopy type. How? Well, if you play the movie backwards, you've inserted a phase along its whole boundary. So this is what in homotopy theory is the attachment of an high-dimensional cell. Okay, now this explains this theorem. Only the critical phases matter up to homotopy. The others can be taken away, actually in the order given by the discrete Morse function. Just do a countdown. Okay? All right. So the goal of these vectors depend heavily on the function, which is, so I've highlighted a complex with a function on it, but you could choose a different function and be less lucky as far as the detection of homotopy is concerned. So the goal is to find discrete Morse functions with as few critical phases as you can. And so in the previous talk, Michael already told you that this in general algorithmically is a hopeless goal in the sense that there's an NP completeness claim. Yeah, it is algorithmic because you could try all possible, but it's NP complete. So Varamita. Is there a question? No. Okay. So in 2012, until 2012 also in general, the belief was that finding discrete Morse functions in general was a very hard task. There's a published paper with this title, Combinatorial Morse Flows Are Hard to Find. This was a probabilistic analysis though, given, I think, something like given all possible matchings, which matching give rise to discrete Morse function. If you use that probability space, it turns out that you're very unlikely to find a discrete Morse function. But this belief that basically this discrete Morse theory was kind of cute, but algorithmically somehow impossible, heuristically also impossible, because finding a discrete Morse function was hard, was overturned. Here you see more quote. So somehow the theory has found beautiful applications, but it has one limitation. Discrete Morse functions are hard to find. It's a direct quote from this paper. So this belief was overturned the next year, because mostly thanks to Frank. Because there was this new method to find a good discrete Morse function, which just consists of 4 commands. It's again a random probabilistic strategy, but the probabilistic space is completely different. So this is the idea. Forget about matchings and forget about functions in general. What you should think about is really as a discrete Morse function, just as a sequence of steps, which are elementary collapses or deletion of top-dimensional phases. So let's do a game as follows. Let's just do elementary collapses until we can. So just look at the free faces, if there is any. If there are free faces, pick one uniformly at random and delete it, and keep going like this. And when you're stuck, and only when you're stuck, let me underline that, when you're stuck doing elementary collapses, when you can do no otherwise, just pick randomly again a top-dimensional phase and kill it. This way you create free faces, possibly. Okay, if not, continue deleting top-dimensional phases. So this is like a 4-line, basically, 4-instruction argument. This has 3 advantages. One is that the probability of getting a discrete Morse function this way is 1. You always get a reduction that is a discrete Morse function. The second is that because we subordinate the deletion of a free phase to the fact that we can do no otherwise, this tends to return discrete Morse function with relatively few critical phases, because we only go, technically, this is this step here. We only arrive to 4. No. Yeah. So this is the key step in the way I phrased it. Does the complex has 3 dimension 1 phases? If yes, we go to 3. And from 3 we go back to 1. So this we never enter 4 unless the only way we could possibly access this 4th line if there are no free codimension 1 phases. So typically we go to step 4 few times. And this is the second advantage. So this tends to give you also the discrete Morse function that reduce a lot. The third advantage is randomness, because if you do things randomly, as opposed to like some algorithms that were cited before, like the Leibniz-Lopez Tavares and so on, if you do a deterministic algorithm, you run it again, you get the same response. If you do a random algorithm, it's like buying a lottery ticket. You run it again, you buy another lottery ticket. You run it 10,000 times, you just bought 10,000 lottery tickets. Except that, apart from the electricity that is paid for by the university, you're not really paying for the lottery ticket, it's free. So, yeah. And so, by running it many, many times, we can also get an understanding of the triangulation. So these are comparison with existing strategies. As you can see that this is considerably faster. It's faster than the algorithm by Michael and Mark Fetch that somehow is the one proving, that's the paper in which they prove this result about NP completeness that was cited before. Alex Engstrom also had an algorithm that was based on basically vertex deletions. So his algorithm is quick, But it goes for a stronger property. For those of you who have heard about this thing, it goes after non-evasiveness, which is a stronger property than collapsibility. So it's able usually to find something quickly, but that's not optimal. And just to give a comparison of the time, you see that this algorithm is very, very quick. On Poincare homology sphere, so I think this strategy, you can ask Michael for details, is not designed to see if there is an optimal vector different than the Betti vector. So it keeps going without, probably this hit the best response, but without realizing it is possible. Again, if you run Alex Enstrom's algorithm, you get 1551, which is so a quick response, but not the optimal one. And for the best answer instead, this new algorithm took 0.02 seconds. As a result, because of this speed, we were able to access. So what happens when you have an algorithm that is faster than, you can access examples that before were thought out of limits. So before the theoretical limit was about triangulations with 50 tetrahedra or so. But after this algorithm, we were able to access things with many more tetrahedron. For example, this guy here, this complex has 300,000 tetrahedron. This was simplified. We found in 3 days of work of some old computer in the building that the optimal discrete Morse vector. And you can also use sometimes, this is not just applied math, you can also use it to prove theorems. For example, all 3 manifolds with less than 11 vertices have optimal discrete Morse vector, actually equal to their Betti vector. So there's 250,000 plus of these guys. The way this theorem was proven is asking the computer for each example to shoot once. So one bullet per manifold. And each time the bullet hit bullseye. So every time, with only one run, the algorithm managed to reduce as much as possible the triangulation. Okay, so this brings me to two things, 2 comments. One is that Frank had a long history of collecting and creating, I wrote collecting, but I should have said also creating, interesting Birchmark triangulations. So we had this project, so somehow, which I'm very happy today to see that it's going to be rescued. So these are some examples by Frank. I collected some, they don't include me mostly, so I only came later, of course, in all this. But these are some examples that Frank created. The smallest knotted sphere is a paper of his from 2004. So this is an example of a sphere that contains on 3 edges, as a subcomplex on 3 edges, a trefoil knot. It doesn't live in R3, so stop trying to visualize it in R3. It turns out that there is a knot, you could have a knot on just 3 edges, the knot being the trefoil, on a suitable triangulation of the 3 sphere. Actually, any knot can be realized with only 3 edges inside some suitable triangulation of S3. But it's really difficult to create these triangulations. So Frank had the smallest one, incredibly small, with some very clever techniques. So this, I should say, this is an example of an unshellable sphere, so non-shellable. But from the point of view of discrete Morse theory, this example is still easy as possible. So it would pass the test by Michael, Mini, Frank, the previous Stokes algorithm, because the best discrete Morse vector is 1001. So it would be recognized by his algorithm. Yeah? So in order to get objects that are not somehow recognizable from the point of view of discrete Morse theory, you just have to increase the complicatedness of the knot. That's what Frank did in 2013. I was a co-author. So he gave the first example of a non-collapsible 3-ball, and also the first 3 sphere in which the best possible discrete Morse vector is not 1, 0, 0, 1, but 1, 1, 1, 1. Okay, so in other words, if you take away a tetrahedron from this 3 sphere, you get a ball that is not collapsible. Okay. The knots were respectively the double trefoil for this and the triple trefoil for this. This is a paper that features A is Karima Di Prassito. With Karima Di Prassito, the first example of a collapsible 5-manifold different than a ball. Because, so basically, it boils down to this. So one way to frame, so okay, so you have this statement somehow. If a manifold let me start like this. If a PL manifold has D manifold, yeah, dimension D, has discrete Morse vector, one, zero, blah, blah, 0, 1, then it's a sphere. This was a theorem in Michael's talk from the previous hour. And there's a similar theorem by Whitehead. So these are both due to Whitehead. There's a similar statement that says that if a PL D manifold with boundary, in this case, with boundary. Otherwise it's impossible. Yeah? Has discrete Morse vector one, zero, blah, 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 0, then it's a ball. Okay, interestingly, so you could ask, is the PL assumptions really needed? This PL assumption is something that concerns the links of all faces being spheres themselves. In general, if you triangulate a manifold, the links of faces are homology spheres. You can prove that they are homology spheres, but you cannot prove that they are really spheres. That's because the technical reason is that you have something called excision in homology, but there is no such thing in homotopy. Yeah, so, you can ask, is it true if I delete the PL assumption? So it turns out that the answer is, without PL, this is true and this is not true. Okay? This is true, this was observed by Forman. It's a very easy proof. The reason is that if you have a contractible manifold and the boundary is a sphere, then it's a ball. And if you take a manifold like that, you take out a tetrahedron, then the boundary is exactly the boundary of the tetrahedron you've taken out. So it's clear that these things is contractible, and it's also clear that the boundary is a sphere because it's a boundary of the tetrahedron you just sucked away. And so from the Poincaré conjecture, then it follows basically that this is true. But it turns out that it's not true. So this was not known. It turns out that it's not true that you can have collapsible manifolds that are not balls. So this last line I wrote is that this is false if you remove the PL assumption. You can have a D manifold that has, actually, when D equals 5, that has discrete Morse vector 1, 0, 0, 0, 0, but it's not a ball. Where is the pointer? The same paper also, yes?
Smallest dimension where it happens is 4, 5?
5. The smallest dimension it can happen is 5. Being below the smallest dimension, it does not. No, I don't think it can work in dimension 4. Yeah. Though I have no quick explanation for it, but I think it's known that it cannot happen in dimension 4. So another result from the same paper is a D complex that has only one free face and it is collapsible nonetheless. So it's collapsible, but only one sequence makes it true. Actually, for this, sorry, you need, so before you ask, this is incorrect as stated. I need to say from D greater or equal than 2, because when the dimension is 1, a collapsible graph is just a tree, and the tree has 2 leaves at least. But from dimension 2 on, basically you have the analog of trees can have the analog of just 1 leaf. And there's also an example in the same paper of a complex with non-unique optimal discrete Morse vector. So it's a contractible complex of dimension, if I remember right, 4, but it can be extended to other dimensions, which has both 1, 1, 1, 0 and 1, 0, 1, 1 as best possible discrete Morse vector, but it's not collapsible. And also in his work, Frank also liked a lot one-parameter families. So in the absolute curvy spheres were explained in the previous talk. You see, I prepared this without knowing the previous talk. The K-blade Socklet complexes was also explained in the previous talk. And being sounds with K-rooms is a tool that actually is explained in the paper I'm going to be speaking about next. Okay, although I will not mention what these are, but Being house with 2 rooms is a classical construction from the 60s. Then Martin Tanzer managed to prove an important NP-completeness result. I forgot if partialability or collapsibility, one of the two. Collapsibility. Oh, thank you. Using Bing's house with 3 rooms. So you can, these are contractible complexes that are not collapsible. But Frank loved to use these examples that one parameter family, but one parameter, the parameter being discrete, one parameter families of examples because they can reveal complicatedness that grows, and so you can test things on them. It's kind of a two-sided things. If you have smart examples, you can use them to test algorithms, and smart algorithms, you can use them to create smart examples. It goes both ways. So in 2018, I gave a talk, and I had to report basically some problem about this algorithm explaining that I highlighted, this discrete Morse theory reduction algorithm that I explained. So this is, by the way, the most beautiful lessons from this is mathematical honesty. Beyond the data is mathematical honesty, particularly when you venture from theoretical math to this type of experimental math. You might be tempted to cook up the data, so because you're reporting that you run on random 100 randomly chosen examples your software, and you see that it worked only 78% of the times, but who forces you to write 78%? A priori, you could write it worked 99% of the times. It's a great algorithm. So instead, what I learned from Frank is an extraordinary honesty. First of all, because people find out, because then later people will rerun your software. But the punishment is not the point. The point is that admitting the limit, being honest and open about the limit of what you have done, is what really enables you to learn. It's kind of like in sports. So if you understand your limits, then you're able to improve. And in particular, so we were interested to use discrete Morse theory for attacking big data from VBA. And Frank became increasingly skeptical about this, and he wrote a paper to explain this thing, and he did software did tests to check this. So whereas I know many scientists, quote unquote, would probably hide this under the carpet and keep asking for grants, saying this is great for big data. But instead, he was trying to see. I think it's difficult to use. Discrete Morse theory works wonderfully, as you have seen from the previous talk, in dimension 3. But it's actually the same paper and the previous talk that made us increasingly skeptical of whether discrete Morse theory can attack high-dimensional data. So you remember the example of Frank, the example Michael about dimension 25 or so. I have somehow another table from their paper. I stole it without permission. Another table from the same paper. This is not a paper that involves me. It involves the previous speaker. But this is running on the 20-dimensional simplex. And you see that you get, you recognize the contractibility only 98.7% of the times. He had a table which featured the complementary number. His table featured 1.3%. That's the difference. Yeah. This was the 20 simplex. I should have gotten a table for the 25 simplex. I don't have it. Then the 25 simplex he showed, I wrote it down, but I forgot. The opposite percentage. So basically, on the 25 simplex, almost. So it's very rare that you can prove collapsibility. I forgot what the number was, but in 92%. 92%. So 8% of the times you are able to reduce the 25. And this is the simplex, guys. So the simplest possible. Yeah, only if you go in dimension 25, even telling that the simplex is contractible becomes an issue. So how could you get around this? And another thing, so the simplex we know, the topology, but we also know of stuff that even to start with, so you're 100% guaranteed in success, right? Because many complexes are contractible but not collapsible, like the done set. You want a one parameter family, these K-blade, saw-blade complexes that Michael spoke about. So there's many examples which are contractible, but if you run discrete Morse theory of them, and you get a response of, the best case scenario is you get a response of the type, well, this is close to collapsible, but I can't say more. Close to contractible. But yeah, I can't say more. No, you get a discrete Morse vector, which is like, I don't know, 1, 10, 10, 1. Maybe it's contractible, but Okay, so this is a slide that I picked from a talk without changing it that I gave in 2018. Well, I changed obviously the title of the slide. And I was saying that we were thinking of incorporating, of changing things. Instead of doing discrete Morse theory, try something different in which you would incorporate random anti-collapses into the model. And so I was asking, is there a random simple-homotopy theory? Any questions? So in the next 5 years, we kept working on it, and so the result that was published posthumously last year is that there is a notion of randomness. It is possible to do randomness, to apply randomness to simple-homotopy theory. So one has to go back to the paper by Whitehead, the original paper that started also the project of Forman on discrete Morse theory. But what is the difficulty? So first of all, what is an anti-collapse? It's just a collapse with a played backwards. Imagine a movie showing a collapse, run it backwards. That's an anti-collapse. Okay, so in dimension 1, if a collapse is stripping a leaf, an anti-collapse is attaching one leaf. But the problem is you have to set up a limit for how much you go up in dimensions, first of all, because a priori it's uncontrollable. Going down in dimension is something that has an end, 0. But going up in dimension, so how up do you want to go? So this is the first thing. You need to figure out a way also to do this randomly. So where do you attach a simplex of dimension above everything that you have? So we came up with some idea that was explored in this paper by trial and error. Oops, I went too fast. So the idea is the following. I can explain it in dimension 2 because it may look... So we look for adjacent faces in the complex. And first of all, we do the same trick that was successful in the discrete Morse theory algorithm. Namely, we only worry about all of this anti-collapse business if we are stuck in performing collapses. So we keep performing elementary collapses. But when we are stuck, we forget about the critical phase business. We want to try something else. Okay? So we try the following thing. We scan the complex for adjacent faces. So if the dimension is 2, basically we want to look for an adjacent pair of triangles. And then there's a technical condition which in dimension 2 can be best explained as follows. I want to attach a tetrahedron on top of this thing. And so tetrahedron will be attached just this way. Yeah? So to attach the tetrahedron and maintain the notion of simplicial complex, the property of being a simplicial complex, I have to make sure that I don't have already this edge in the triangulation. That's it. So just make sure that prepare the example in such a way that whenever you see two adjacent triangles, I want only a pair of adjacent triangles such that the opposite vertices are not already connected by an edge. Because what I plan is to introduce one such edge. Clear? So look for a pair of adjacent triangles such that you don't have in the triangulation already the edge, an edge inside or so connecting these two. So there's already a comment here that maybe there is no such thing. I'll deal about this later. So if you find this thing though, then we do the following. We attach a tetrahedron like this, yeah? I'm simplifying a bit, but this is the idea. We attach a tetrahedron, this goes up in dimension. One more. And then immediately after the attachment of this tetrahedron, we remove the tetrahedron we just attached, but paired with a different triangle. Paired with one of the two triangles we had already. Okay, so either these give names. So we add 1, 2, 3, 4, and then we do an elementary collapse. Delete 1, 2, 3, 4 with either 1, 2, 3 or 2, 3, 4. So delete it with one of the triangles that was already present in the complex, not with one of the triangles that you just inserted. Why? Because otherwise you go back to where you started. Yeah? We don't want to end up doing nothing. Okay, so if you collapse it away with like 1, 3, 4, and then you collapse away this triangle, you're exactly back at square one. So, but instead we collapse it with So this is the idea. It's a bit more complicated than this. But notice that since we add the dimension, but just for a fraction of seconds, then immediately we killed the new simplest introduced. Basically, the dimension stays constant. So we solve this problem of like, oh, but the dimension could go up to infinity. No, because it goes up by 1, and then in the next step, it goes down again. So basically, this double step does not increase the dimension. How do we deal with the issue that perhaps there is no such thing as two adjacent facets such that induced, what is the condition here, this thing? The induced subcomplex on the combined D plus 2 vertices is purely dimensional. Okay, the way we deal with it, we just subdivide the face, which is somehow nicer. It fits nicely to this theory because the stellar subdivision, word from this morning, the stellar subdivision of a face, looks like this in dimension 2. This stellar subdivision can also be thought of as the result of the attachment of a tetrahedron and then the collapse of this tetrahedron with the base. So it also looks like a step of the type, if you think about it. This stellar subdivision could be thought of, well, I add the tetrahedron here, and then immediately afterwards, I collapse away with this tetrahedron with the triangle originally to be subdivided. And then you get exactly this, no? Because from here to here is like toggling from above to below in the picture of a tetrahedral pyramid. How much time do I have? 15 minutes?
20 minutes.
20. I'll try to take 15 so you won't get too hungry.
No, 15 here. I mean,
Okay.
formally 15, but in reality we.
You don't want to eat.
No. We start a little bit later.
All right. So this is the other. I haven't hidden anything under the carpet. It's longer than the other one, all right, but it's not tremendously long. And let me show you maybe an example. So this is the done set. So maybe you recall that I maybe haven't said it. On the done set is not collapsible. So if when you run discrete Morse theory on it, it turns out that 1, 1, 1 is the best possible vector you can get. Now, if you tell me this 1, 1, 1, I can't really use it to say that this is contractible, because there are also non-contractible things that have 1, 1, 1 as discrete Morse vector. So this is one example in which you have no proof of contractibility via discrete Morse theory. Instead, with this anti-collapsing business, you have a certificate of contractibility immediately. You only need one anti-collapse. So this is the picture. It's a bit more complicated than this because we use 3 triangles, but you can, So you see that I add the tetrahedron 1, 3, 6, 7, and then I immediately afterwards collapse it using the triangle 1, 3, 6 that was already present. Instead, basically, in the end, I traded the triangle 1, 3, 6 with a triangle here called 3, 6, 7 that was not present in the beginning. This trade is very fruitful because now this new complex is collapsible. So with one anti-collapsing step, you decided contractibility. So if you test the Abalon, you need 3 anti-collapses. If you test Bing's house with k rooms, that's the F vector. And it turns out that on this infinite family, we can prove that only 6 expansions are necessary. 6 cleverly chosen. If instead you use randomness is like stupidity. Like random is a bad mathematical word to say stupidity. If you use randomness, it goes up with k. But if you're clever, no matter what k is, you only need 6. 6 anti-collapses show that Bing's house with k rooms, no matter what k is contractible. This sentence, I have to really read it because if you make small variations, it becomes false. So we don't know of a complex whose contractibility cannot be recognized by this software. I'm not claiming there is none. I'm claiming we don't know of any. Okay. The truth is, there is a theorem by Whitehead that says that so any contractible complex can be deformed to a point with a sequence of collapses and anti-collapses. But, so our collapses and anti-collapses are special in 2 ways. One is that we only go up by one in dimension, and already this restriction is unclear. I think it's an open problem, a major open problem. If you can just going up by one in dimension, reduce every contractible complex to a point. It's equivalent to a famous conjecture, whose name now escapes me, Andera something. Yeah. But a priori, this would not be a major difficulty because we could modify this algorithm and go up 2 in dimensions. The other, though, main thing is that in our algorithm, we only perform anti-collapses when we are stuck doing elementary collapses. That's a choice. And I don't know if Whitehead's result applies to this particular choice. Yeah, so Whitehead says any contractible complex can be reduced to a point by a sequence of collapses and anti-collapses full stop. It doesn't say so that you do collapses only, do anti-collapses only when you're stuck doing collapses, and you go up only 1 in dimension, and the collapses, anti-collapses are of this type. If you keep adding conditions, it becomes force at some point. However, what I can say is that on all of the examples that we have available from theory, I see no reasons to doubt, either I see no reason to doubt, or directly we tried and it recognized contractibility. We don't have a single example in which now this one fails. In contrast, we have many families in which contractibility is not read off by discrete Morse theory. Many. Even the 25 simplex, thanks to the work of Michael. I should also say that this lifts another well-known algorithm that was mentioned in the previous talk, bistellar flips. So if you have a surface, closed surface, yeah, and you try this algorithm, so you have no free face because it's a surface, closed surface, so you have no free edge. So what you're trying to do is, well, you're going to be finding 2 triangles in the boundary, and then attaching the simplex, and then doing if you think about it, what happens is exactly a bistellar flip. So these are exactly the 2 cases. So basically, if you apply to close the manifolds with no boundary, and the dimension is close enough because we want to have, there's some stuff to reduce, then basically this is equivalent to this program is just doing bistellar flips. So this is generalization of bistellar flips however, this is only true for dimension smaller or equal than 6. Yeah, so this, if you on a surface, for example, what we're doing is exactly bistellar flips. But this applies to arbitrary complexes, of course. Some results, so before I conclude my talk. So here are some empirical results in the style of Frank. I will produce this type of tables. You can see these are empirical and not theoretical. And you can see the difference right away. Being housed with k rooms, you can see that here the number of expansions increases, but I told you that 6 were only necessary. That's because 6 is theoretical. This is practical, doing random choices. So 6, if you cleverly pick the anti-collapse. If you pick them randomly like a monkey, this goes up with k. Okay? However, you can see the comparison between the f vector and the number of expansions. And as you can see, this is reasonably close. So, for example, this is a ball that contains, this contains a triple trefoil realized with just one edge or so, plus a boundary path that takes you back. And as you can see, so actually you cannot see it from here, but on all of these examples, so maybe I should say, better that I say like this, all of these examples are not collapsible. So for none of these examples, I'm able, using discrete Morse theory, to convince you that it's contractible. But I can, with this number of expansions found practically, ignoring completely somehow cleverness and so on, just run it and you get 95 anti-collapses. This is good. Another thing that it could be used on is, well, okay, so this is another, these are the type of weird examples that would pop up when you collapse a simplex. Again, for all of them, it's easy to see that they are contractible using this new strategies, this random simple-homotopy theory. Collapses and anti-collapses. So you see that here the number of expansions is relatively small. Yeah, this we also recorded the minimum. So these are all, what are these examples here? This is the leftovers of collapsing away like a D simplex, D grows. So like D equals 14 means we try to collapse the 14 simplex. We get stuck at examples that are contractible but not collapsible, and we just put them in an archive. All that we find, we sample them. And then later we try to see, okay, what about the random simple-homotopy theory on those? Discrete Morse theory on those examples fails because they're not collapsible. There's no free face. What about random simple-homotopy theory? Does this work better? The answer is, well, for all of them, we were able to decide contractibility. All of them are digestible rather quickly. A final thing that I want to say, I really managed to cover all topics, so even you see that the counter has gone up. So I had prepared like extra slides, but yeah. So this performs also well when you have a substructure to recognize. For example, if something's sitting inside something else. Yeah, so this random simple-homotopy theory manages to detect these substructures that have the same homotopy type. We have one example, yeah, which is as follows. So the example is like this. We took a surface of very large genus, and now we thickened it. We tried to manipulate it in a way that made it more combinatorially complicated while remaining topologically trivial. So the way we did so is as follows. We added random vertices with subdivisions. We performed 200,000 random edge flips. And then we took a cross product with like a 5-dimensional, basically, cube, prism, or something like that. So the result is a thickening of the original surface. So from the point of view of topology, just thicken its original surface cross some trivial space. Yeah? Cross like 5 cube. It's not a 5 cube, but topologically, 5 cube. Okay, so if you run this, however, the computer did not know what surface we started with. So we took this giant complex, which is now 7-dimensional, it has 34 million faces, and we fed it to can you recognize the original surface? And the answer is yes. In an hour, with a few thousand expansions, but in an hour, the original surface was recognized. So we tried again and again and again. Every time, out of 100 times, this surface could be recognized. So I don't know, I now have no drawbacks to present to you, but if I had, I would. Yeah? So honesty is important. At the moment, I don't see, I think this is could be a better tool to tackle data that is high dimensional than discrete Morse theory, but so somehow. I'm waiting for the drawbacks. The moment I will know drawbacks, I will present them to you because that's what I learned from Frank. And here, this is my last slide. Those weird abbreviations that you have seen are these papers here. So if you want to figure out exactly where is where, I'm happy now to take questions. Thank you for the attention. And yeah, I'm happy to take questions. These are the papers that I'm talking about.